Okay, so let's move on to Chapter 7. Chapter 7 is transmission line for communication. Well, to put it in short is, in this chapter we will perform the so-called steady-state analysis, especially in the time frequency domain. So Chapter 6 is time domain transient analysis. And Chapter 7 is related to frequency domain steady-state analysis of the transmission line. So we are all looking into transmission line, but Chapter 6, the time domain analysis provides a more convenient means for you to understand how signals goes on in the transmission line. But in reality, in the design of microwave circuit, we are less prone to perform analysis in the time domain. So in reality, we tend to use frequency domain analysis for the design of microwave circuit, transmission line circuit. And for frequency domain analysis, we assume the signal is a sinusoidal signal. This complies with modern wireless communication requirements, because in modern wireless communication, all the signals are, all the information, most of all the information are modulated, are modulated to a so-called carrier frequency, 载频, 载波. For example, if you are listening to FM radio, you have the so-called FM or AM frequency modulated or amplitude modulated signals, and amplitude modulation is kind of primitive because the audio signals is directly modulated as the magnitudes of the signal in AM signal. So AM is relatively narrow banded, and for frequency modulated signal, there is a small frequency shift in its carrier frequency. So when we refer to a radio station, say ICRT in Taipei, the frequency is 107 megahertz, 100.7 megahertz. But if you receive the signal and observe the signal with a spectral analyzer, you will see that of course the signal peaks at 100.7 megahertz, but it will have some spread. The signal will spread for a certain bandwidth around 100.7 megahertz, okay? Because the audio signal are modulated as the shift in the carrier frequency. But the width of the signal represents the energy content of the transmission. Then of course, FM and AM technology has been invented for more than 6 or 7 decades. So they are techniques invented nearly 100 years ago. For modern wireless communication techniques, such as the mobile phone or the Wi-Fi signal, they adopt a more sophisticated, more complicated modulation scheme. For example, have you heard of the Have you heard of PSK? PSK, phase shift keying. So which means the signal is, the information is represented with 1 and -1 on the so-called constellation plane. That is the signal phase on the complex plane. Then we have the QPSK. So which means you can divide the signal into 4 quadrants. So what is the advantage of moving from PSK to QPSK? Well, you can transfer 1 more bit at the same time. So you have then we have the so-called 16 quant. Q is QPSK, A is amplitude. So you can further divide the constellation into 16 points on the complex plane, which means you can deliver 4 bits at 1 time interval. Then you will have 64 quant, 128 quant, about 256quant or1024quant之类的所以现在新的那个，但问题是什么？当你的那个框越来越大的时候，这边就会挤在一起了所以 so if you evolves into higher order modulation scheme, you need to ensure that your channel, your signal propagation channel is of good quality. Otherwise, the signal will mix up together or will be interfered by noise, and you won't receive anything. You receive just garbage. Okay. On the other hand, if your channel quality is good, you can have very higher order modulation scheme. So how come I end up with this discussion? 为什么会讲到这边去 ？OK， 好啦，那个，所以好，我要讲的事情就是那个，现代的那个无线通讯里头，其实有例外啦，大部分的通讯都是载频的啦，都是要依靠一个特定的 carrier frequency， 但是有原则就有例外嘛，对不对？所谓的例外就是像是所谓的展频通讯或超宽频通讯，传统的通讯的话，你就有一个固定的频率，所以那些5G、4G、5G 的那个时代，电信公司要花几百亿去标特定的频段，那这样子的话，他们的讯号就是走那个特定的频率。那有特定的频率，当然好处是，就只有你可以用嘛，别人不能用。但坏处是，只要别人坏人想要干扰你的话，我就针对你的频率去发一些讯号，让你的讯号就没办法传送了嘛。就像前一阵子不是有无人机吗？大家在讲说用石头打还是用喷水枪还是用什么比较好，但其实有人说，你就发个那个 GPS 信号 1.575 的讯号盖台，然后那个无人机它就不知，它的那个 GPS 讯号被盖台之后，它就在那边讲说我是谁，我在哪里，然后它就会跑掉，或者是就直接降落了，一般的那个娱乐用的那个无人机它只要收不到 GPS 讯号，它基本上会直接降落。好，所以载频通讯的坏处就是容易被干扰，所以有所谓的超宽频通讯。超宽频通讯它讯号打起来就是啪啪啪啪啪， 啪啪啪啪啪。那所以它的讯号都是脉冲的。那脉冲是什么？它出现的时间很短。那意思是什么？它在 frequency domain、time domain 上面出现的时间很短，那意味着就是它在 frequency domain 上面它的能量分布是很广的。所以你假如用一个 spectral analyzer 频谱分析仪去看你收到的那个啪啪啪啪的音炮讯号，它看起来就跟 noise 差不多。那就变成什么？你要知道我当初打出去的音 pulse 它是怎么样拆解成不同频率的内容。那你只要知道的话，那你就可以把它重组回来。比如说前面那一段可能是相位是0度，然后中间那一段你要去乘上一个180度的相位，这一段要乘上90度的相位。当你用正确的那个相位把它们重新加在一起的时候，你就会得到原来分解送出去的讯号。所以这种叫做超宽频通讯 （Ultra Wideband Communication）， 它把讯号要传送的讯号的能量散布在频谱当中。那这个技术其实都军用的啦。那最早的商业化是 Intel 提出的。Intel 大概在20年前提出一个规格叫做 UWB Ultra Wideband 的规格。那当初它的目标是拿来做PLAN Personal Area Network 是不是 PAN P， 就是说它当初那个 UWB 那个规格是在跟 Bluetooth 抢市场。所以本来他们 Intel 讲说他推这个规格，那短距离的无线传输连接可以用这个东西来去做。不过反正事情给 Intel 去推，通常都会失败。像很久以前有一个规格叫 WiMax， 它是跟 WiFi 在它是跟谁在竞争 ？WiMax 是跟谁在竞争？跟行动通讯在竞争，它也是 Intel 在推的。然后造成的结果是台湾有几家公司破产了。因为后来 Intel 说，我不要玩了就不要乱杠啊，这应该不要，今天这些人不要放上去所以后来那个 UWB 也是 Intel 也说不玩了，但最近又拿出来了，最近又拿出来讲了，因为它有保密的那个安全性、保密的那个优点在那边。为什么讲到这个啊？好啦所以假如你是窄频通讯的话，那其实宽频通讯宽频的讯号在传输线里头的分析就会变得很复杂。所以为什么 Intel 当初推不下去因为就只有他会大家合作厂商不好搞，那个元件很贵，因为你都要变成宽频的元件但目前的那个通讯系统的主流，大部分都还是特定的频段还是相对窄频的元件所以我们今天在第7章里头要学的传输线分析frequency domain analysis 还是针对在特定频率，所以你会看到我们的讯号都是用phasor来表示的意思就是说我们大家你知我知我们现在在讨论的是某个特定频率，比如说 1.575 GHz 的讯号所以那个 time dependence 我们就不明写，但是你要知道那个 exponential j omega t 那个描述时间跟频率关系的那个 exponential， 事实上就在我们的讯号里头，只是我们没有把它明显写出来而已。OK， Alright, so go back to the content of the chapter 7. We are similar to the transient analysis. In the steady state, there should be forward going and reverse going signals on the transmission line. And the observation made on the transmission line, even in the steady state, may contain forward going and reverse going signal. That would be the summation of the forward going and reverse going signal. And so in the steady state, the voltage and current observed can be regarded as dimension of sinusoidal signal. And in section 7.1, we will discuss the so-called standing wave concept. This is a very important physical phenomenon which is not only related to the electromagnetic wave. The standing wave concept is also important in terms of acoustics or optics in many wave-related topics. And in section 7.3 and 4, we will introduce the Smith chart, which is an important tool for transmission line design. Okay, so in section 7.1, we will look into the so-called short circuit line. So, here is the review of the transmission line equation that we have observed before. In chapter 6, we already shown that electrical field intensity and magnetic field intensity, that is the E and H fields, can be replaced with voltage and current signal, so that the transmission line problem can be analyzed as a one-dimensional wave propagating problem. So for voltage and current signals, because they are the so-called one-dimensional wave equation, the solution will appear in the form of AF plus BG. Okay, so it can be decomposed into forward-going component and reverse-going component. So A is a constant, and F is the function of the forward-going signal. In this case, the F function is replaced with cosine omega t minus z over Vp plus sigma. So the most critical part in this equation is the parameter t minus z over Vp. Why? Because in this parameter, t minus z over Vp, we mingle the concept of time and position, t and z. So in this parameter, both time and location are specified. And if you take in the derivative of t minus z over Vp, you will end up with the velocity of a signal propagation, which is Vp. 所以它的重点在于对于一个能够传播、能够跑起来的波来讲，它的描述这一个波动的方程式，它的变数必须要同时带有位置跟时间的描述。所以你在里面看到的 t 减去 z over Vp 就同时有时间跟位置的描述。你只要把这个描述去取微分的话，你还会得到，然后你去找位置相对于时间的变化的话，你会得到它的速度 Vp 嘛。好，那换过来讲，假如 t 跟 z 空间跟时间的描述没有出现在同一个函数里头，没有出现在同一个方式里头，它就没有办法形成跑起来的波。好，我们接下来讨论到驻波 standing wave 的时候，你就会看为什么会这样讲。OK， all right, so equation 7.1a and b shows that both the voltage and current signal can be divided into forward-going part and reverse-going part. And we know one important characteristic about the wave in transmission line is the velocity of propagation, Vp over here. The other important characteristic about signal in transmission line is the characteristic impedance that can be, which can be interpreted as the ratio of voltage over current. And the characteristic impedance can also be found as the square root of per unit wavelength, per unit length inductance over per unit length capacitance, as you see here. Now, and one thing that you need to remember is Vp, the velocity of propagation, cannot be changed for a specific type of transmission line because it's determined by the material used to form the transmission line. The product of L and C is the same as the product of permittivity and permeability. On the other hand, the characteristic impedance can be modified by changing the geometry of the transmission line. Okay, so you can form a transmission line of 100 ohm characteristic impedance or 50 ohm characteristic impedance, providing that the geometry of the transmission line can be adjusted. All right. So similar to the to simplify the expression for these two signals, we use relationship. We use the phasor representation. Okay, sorry. 7.2 A and B are the same transmission line equation, while the instantaneous form. You see, this is instantaneous form because for V and I, they are function of position Z and time T as well. Now, they are the function of Z and T. But here, for phasor representation, they are only function of Z. There are no dependence of T explicitly 没有直接明写，但是有啊。Of course it had time dependence. That would be the exponential j omega t terms. But we didn't show. We do not show them explicitly. Okay, so it's just so you only see the location or position dependence for phasor representation. Okay. But you can find out the instantaneous, you can convert the phasor representation into instantaneous form by times it with the exponential j omega t term and taking the real part of that. Okay. So before we proceed for discussion in 7.1, another thing that you need to notice is we introduce another parameter D. D is the distance measured from the right. In chapter 6, we use Z to address the position on the transmission line. And Z equal to 0 on the left-hand side. And on the right-hand side, we mark Z equals to L, the length of the transmission line. Because in chapter 6, we are interested about the signal generated from the generator, which begins from the left. But in chapter 7, we are more interested about the termination. So we are more focusing on the right-hand side. So therefore, we introduce another parameter D, the distance from the load, the distance to the load, to address the transmission line equation. So by adopt the position dependence as D, the transmission line equation can be modified as 7.3 A and B, so that will be the positive going part, the forward going part, and the reverse going part. Okay, remember, if we use Z to prescribe the forward going component, that will be V plus times exponential minus J beta Z. Minus J beta Z. However, in this case, we are measured from the right. So the forward-going signal, that is, travel to negative D direction, is expressed as exponential plus J beta D. And the reverse going part is addressed as V minus times exponential minus J beta D. Okay, so be careful about the location parameter D. Okay, so we need to change the sign for the two components. So supposing that on the left-hand side there is a sinusoidal time variant traveling wave exists on the line due to the source, which is not shown in the figure, but the condition have reached the so-called steady state. So which means the sinusoidal signal source has appeared on the transmission line for a certain amount of time. So the signal have already reached the so-called steady state. Then we are interested about the signal distribution on the transmission line. In particular, we begin with a relatively simple example. That is, the right hand, the end of the transmission line is terminated with a short, which means all the incident energy are reflected, which means the total voltage on D equal to 0 should remain as 0 at any time, And here is the total voltage expression for total voltage, which has the forward traveling part and reverse traveling part. But for this specific case, the end is terminated with a short. So we can, if you supply this boundary condition that at D equal to 0, the voltage always 0, it's 0 always, then we can end up with this result. The V minus signal, the magnitude of V minus should be equal to the V plus signal, and they are different in polarity, which V minus is the minus of V plus. And you can tell the reflection coefficient is what? -1, which is consistent for short circuit termination. The reflected wave is just the opposite of the incident wave. Okay. And for a position away from the termination, that is, the position is D, the total voltage, which contains the forward going part and reverse going part, can be expressed in 7.6. Note, we replace V minus signal over here with the minus of V plus. By doing that, we can take out V plus from the first and second term. And the remaining term, that is E exponential J beta D minus exponential minus J beta B, can be rewritten as a sine function. That will be 2 times J times sine beta D. If you do the same thing for the current signal part, originally this is minus V minus, and we can replace it with plus V plus like this. Then we can collect the V plus term to the front, and the remaining part, exponential J beta D plus exponential minus j beta d can be rewritten as cosine beta d. So in the red box are the total voltage on a short terminated transmission line and total current on a short terminated transmission line. And they appears in sine and cosine function. So what is the implication of this result? The voltage on the short terminated transmission line, the voltage signal and the current signal are different. Let me put it another way. Let me try again. There is a 90-degree phase difference between the voltage and current signal on a short terminated transmission line. Okay, now because the voltage and currents are represented with sine and cosine function. Now, so this current, sorry. These are phasor representation. We can rewrite total voltage and total current in instantaneous form. And we can do that by times the phasor form representation of voltage and total current with exponential j omega t and taking the real part. So you ended up with this result. Okay? Be very careful about that, about this derivation. Okay, from very top, you times exponential j omega t, and you replace v of t with 2 times jv plus sine beta d. And j is replaced with exponential j times pi over 2. And the v plus signal, which in general is a complex number, is represented with the magnitude part and the phase part. So it's written as absolute value of v plus times exponential j theta, the phase of the v plus signal, and followed by sine beta d and exponential j omega t. So you see there are 3 exponential in this expression. Exponential of j pi over 2, exponential of j theta, and exponential of j omega t. So we collect the 3 terms together as omega t plus theta plus half of pi. And because we eventually take in the real part of this exponential signal, so it turns out to be cosine of omega t plus theta plus pi over 2. And this thing, sine beta d, is left here, and the absolute value of v plus is leaving out here. And you can take out the pi over 2 part by changing the cosine function into sine function like this. Okay? So that is the total voltage on a short terminated transmission line. So what are the important observations about this result? How about the description about location? How about the description about time? The description about location appears in the first sinusoidal function, sine beta d. The description about time appears in the second sinusoidal equation, that is sine omega t plus sigma. So they are separated into 2 functions. They are not staying in the same function, which means they cannot comply with the requirement of traveling wave. Wave cannot go on like a traveling wave. So this is referred as the standing wave because they are not traveling. They dents on the transmission line. Okay, so you can do the same thing for the current distribution, and it turns out to be cosine beta t times cosine omega t plus theta. So again, the location description t and the time description t are separated, appears in different function. So you don't have a joint description about position and time. So their properties, they are no longer traveling waves. And another thing to be noticed is that there is a 90-degree phase difference between the total voltage and total current signal. So here is another perspective that we can view the result. If we write up the power density description about the signals, that's power density or power, sorry. Because P of dt equals to the product of voltage and current, so it's the power, not power density. 电场乘磁场的话是 power density， 电压乘电流的话就是 power 了。So if you do the product of the total voltage and total current, we have sine beta d, cosine beta d, sine omega t plus theta, and cosine omega t plus theta. So you can collect first two terms and the last two terms. The first two terms appear as sine 2 times beta d over 2, and the last two terms become sine 2 times omega t plus theta over 2. Okay, so the 2 and 2 in the denominator cancels from the 4 on the denominator. And again, is that a traveling wave? Is that a propagating wave? No, because the position description and the time description appears in different sinusoidal function. Okay, so the overall voltage and current behavior, the energy, is not a traveling wave as well. So the energy cannot propagate. The energy cannot propagate. However, if you view the signal individually, you have traveling waves going from left to right, the incident signal. And you also have a traveling wave going from right to left, the reflected signal. However, because their magnitude are the same, they are out of phase. When you do the summation of the two, it becomes the so-called standing wave, which is not traveling. Okay? Why we say that it is not traveling? Because if you look at if you plot the total voltage on the spatial domain, be careful about here. The vertical axis is the amount of voltage. The horizontal axis is the distance from the right end. So this is remarked at 0. Well, this is the axis of D. 横轴是空间，这是空间。And because the total voltage can be separated into it can be regarded as the product multiplication of sine beta d and sine omega t plus theta. It can be drawn like this. 所以这边我们看到为什么图会画成这个样子。所以我们是试着把 sin 贝塔 d 跟 sin 欧米伽 t 加西塔这两个方选同时画出来。所以你会看到这边有一些线，然后 mark 1、2、3、4、5、6、7、8、9，这个上下震荡的那个线， 是用来表示后面的那个 sin 欧米伽 t 加西塔，啊，所以在不同的欧米伽 t 加西塔，也就是在不同的相位，它的这个 sin function 可能是整个平的，啊，在某些时间点呢，它会往上涨，某些时间点呢，它会往下涨，啊，往上往下涨。那 sin 贝塔 d 的影响在哪里？sin 贝塔 d 的影响在于横轴的那个变动。你会看到，在这一个图形上面有所谓的节点 node。Zero voltage node， 那是出现在哪里？出现在贝塔 d 等于派的整数倍，啊，因为对于 sin function 来讲，贝塔 d 等于0的时候 ，sin 贝塔 d 等于0；贝塔 d 等于派的时候，也就是180度的180度的时候，它也会等于0；360度、540度，啊，所以贝塔 d 等于 m 派的整数倍的时候，你会遇到一个讯号的电压讯号的节点。那你只要把贝塔用 2 pi over lambda 写出来的话，那 d 就会等于是2分之 m，2分之 lambda 的 m 倍，也就是节点出现的那个位置会出现在半个波长的整数倍。所以从右边开始往左边看，每间隔半个波长就会出现一个电压的节点，而第一个电压的节点会出现在传输线的最右边，有没有？好，所以这是我们根据终端短路传输线的电压关系式所画出来的结果。那这些地方我们刚才讲过了哈，因为贝塔 d 等于派的整数倍，或者是说距离 d 呢是2分之 lambda 的整数倍，所以你会出现电压的节点。而在电压节点之间，电压值还会随时间变化，所以它会上下震荡。那这个的影响就由 sin 的欧米伽 t 加西塔来去描述。然后在这个电压节点的地方，我们要留意到它会是能量的节点，因为能量怎么算？那个 P 我们刚刚怎么算的？是电压乘上电流嘛。那这个点的电压怎样？Always zero， 所以你在算 P 的时候，这个地方也会是能量的节点，也就是 P 在这个地方永远等于0，I3 艺术，能量过不去了，能量过不去了，哦，能量没有办法从左边流到右边，或者右边流到左边，因为这一个点上面的 P 永远等于0。那假如你去看电流的变化，我们试着把这边讲完哈。因为电压变化的话，你看到节点是由 sin 贝塔 d 所控制的。电流的话，它是 cos 贝塔 d 跟 cos 欧米伽 t 加西塔。后面那个是看时间变化，所以它一样上下震荡。那你会看到电流的节点会出现在 cos 贝塔 d， 所以它会是什么？2分之应该说贝塔 d 等于2分之派的基数倍的时候，就会出现电流的节点，然后它的间隔也是半个波长，好，但是你注意到，因为一个是 cos 贝塔 d， 上面是 cos 贝塔 d， 所以它们的节点出现的位置刚好会是在电流节点出现的位置会在电压节点的中间，所以假如你把上面的电压跟下面的中间的电流乘在一起的话，下面这个就是你的能量的那个变动，然后你会看到能量的零点、能量的节点的频率会出现会被 double，为什么？因为电压的节点是能量的节点，电流的节点也是能量的节点，所以每隔1/4个lambda，每隔1/4个lambda，你就会出现一个能量的节点。好，那换句话来讲 P 的关系是 sin 的2贝塔 d， 所以我要这个2也就告诉说你的节点的那个数量会多1倍，所以对于 standing wave 来讲，所以这张图有没有看到？我们看下一张啦 ，OK， 这张图可能比较清楚。黄色线是 V plus signal， 灰色线是 V minus signal。那个桃红色线是 V plus 加上 V minus， 好，所以你光看黄色线它是 troubling wave， 光看灰色线它也是 troubling wave， 但 V plus 加上 V minus 会是 standing wave，OK， 好，这个动画回去可以自己看好，不要秀太久哦，因为转档的时候它会变好，会拖好久 ，OK 啊。So in particular, we represent the so-called complete standing wave in view of the zeros, amplitude, and the for voltage, current, and the power at a certain location. So if you have 0 voltage, 0 current, and 0 power, then they are referred as the total, complete standing wave, 完全驻波，这个词稍微记一下。因为有完全驻波就有不完全驻波，意思就是说 V plus V minus 比 V plus 小的时候，它们加起来就不会刚好等于0，所以那个称之为不完全驻波。而完全驻波呢，就是 V plus 跟 V minus 的 magnitude 相同，所以它的一个要求就是说你的 termination 会是不吃能量的，像是 short。open 可不可以 ？open 也可以。inductor 可不可以？纯 inductor 也可以，纯 capacitor 也可以。所以只要你不吃能量的话，能量会被弹回来的话，你就会形成完全驻波。所以这边我们最后讲的，等大小的前行波跟后退波就可以形成完全驻波。好，不好意思，我们今天到这边。